Mesh/loop analysis with current sources. If a circuit contains a current source and loop analysis is applied, the location of the current source will tell us how to modify the loop equations. There are two possible positions or locations. One, we have current sources isolated from other loops, and then the opposite case where you have current sources in between two loops. So what I want to do here is that I'm going to show you these two possible locations in this example circuit. So in this example circuit, we want to determine the loop currents. So let's do this here. So I'm going to have a current source. With a series of resistors. And let's give values to these guys. So I'll call this 10 milliamps. This one will be 20 milliamps. And then I have these resistors. So what I want to do here is that I want to start analyzing this circuit. And the way I'm going to analyze it is that the first step that we do is that we apply regular mesh analysis. And the way we'll do this here is we'll do the following thing. We're going to apply step one. And in step one, we always do the numbers. So let's do the numbers or the counting. So we see that there are 3 loops, three independent loops. And I want to be careful when I say those independent loops, because we're going to have to modify that. But typically we say that if there are 3 independent loops, then there are 3 loop equations. This is what we've set up to now. So now if I come in and I put that circuit back in right here, let's say this is it right here. I'm then going to come in here and I'm going to say, okay, here's my first loop, and I'll call that 1. My second loop, I'll call that 2. And then I have this third loop, which I'll call 3. But what you're seeing here is that if I do the numbers, we should then have 3 loop equations and 3 unknowns. And in this case, we would call them I1, I2, and I3. But we have sources. And one of the things that you see here is that I would call this an isolated source from the language that we used above, because this 10 milliamps is not connected to loop 2. However, if you look at this circuit right here, or this current source, this one connects loops 2 and 3 together. So as a consequence, these current sources have to change the number of loops to solve for. So these 2 current sources will change the number of required loop equations. And that's the reason why I put the quotes up here. You're going to see that they're not completely independent anymore. So let's go do that. So we'll take each source one at a time. So if you look at the first source, which is the 10 milliamp, then I'm going to say that I'm going to focus on the 10 milliamp source is isolated. Now, because it's isolated, ACL forces I1 to be exactly the same value as the current source. So what we could say here is that from KCL, 1 immediately concludes that this current I1 must equal minus 10 milliamps. It forces it to be in this situation. So what I'm saying here is that the 10 milliamp current source reduced the number of unknown loop currents. So this isolated current source reduces the number of unknown loop currents. So if we continue with our numbers, I started off with 3 loops. Now I'm going to subtract one of these, and this one is 1, and this guy's due to what? This is due to the 10 milliamp source. So it's reduced that. And so now, instead of 3 loops, we now have 2 unknown loop currents. So if I look at what I'm seeing here, then my current is that I have I2 and I have, oops, wrong color. It's going to be I2 and this is going to be I3. So now let's go focus on the next circuit here, or the next source. So now the next one is the 20 milliamp source connects loops 2 and 3 together. So if I come in here and I place this circuit back in, so we now know that we have I1, but I1 here is really minus 10 milliamps. So we know that's a known source, but now we have I2, and of course we have I3. And so the first thing that we see here is that the location, the location of the 20 milliamp source sets up a special situation. Since currents I2 and I3 are not independent anymore, but dependent via KCL. So what we want to do here is that we want to pick a current source, a node that allows us to look at that. There's 2 ways to look at that. So what I'm going to do here is that I'm going to look at this yellow node right here. And so when I look at this yellow node, what is it that we see here? Well, if we apply KCL, let me move this up a little bit. So what we're going to do here is that we want to apply KCL at the yellow node. And there's 2 ways of looking at this. So what we're going to see here is that I have this resistor. I have this current source. And then this resistor right here. And what we're seeing here is that this is what we called 4K, and this guy is 6K. And so here's my yellow node right here. So when I look at the current, you see here is that I have the current I2. I have the current I3 going in that direction, but I have 20 milliamps also going into that node. So if I look at this, what I'm seeing here is that if I look at the current coming in and the current coming out, then that tells me that the currents coming in is going to be the 20 milliamp plus I2, and then I'm going to get I3, and it's going to equal it. And one of the things that I don't like about this way, even though it's totally legit, this is not in matrix form. So what I propose is looking at this slightly different. So what we'll do here is that we want to focus on the current source. And when you look at the current source, it really looks like this. So if you look at the current source, look what's happening. Our loops show that we have to have what? Our loop shows that I2 is coming down in this direction, right? That's I2. And even though I didn't write it, we know that's 20 milliamps. But now look at I1 or I3. I3 is going up. So if you look at this thing here, the 20 amps and the I3 are both in the same direction. So what we write then is we then say that I3, we're going to call, that's going to be the positive direction, that's going to be the negative direction. So then I'm going to have that I3 minus I2, because they're not in the same direction, that has to equal 20 milliamps. And I say that this is what we want, because this here is in matrix form. And this is what we call the supercondition, which I haven't defined yet, but that's what we're looking at here. So I'm going to move this up just a little bit. So now what we're seeing here is that because I2 and I3 are dependent upon each other. What do I mean here? So if I know the value of 2, I automatically know the value of 3. So they are literally dependent upon each other. These two loops form a super loop. Just like two dependent nodes form a supernode. And is identified by drawing a dashed loop. Just like we did with nodes. That circumnavigates both loops. That is, there are not, there are no two loops, but one super loop. So if I come in here and I take this circuit and I copy it and I bring it back down here. So since we already know what loop 1 is, then I'm going to come in here and I'm going to say, so I'm going to take off this yellow here. Then I'm going to come in here and I'm going to say, so now I have a super loop that goes around like this, and they go in the same direction as these guys. So this guy right here is the super loop. So now, with each super loop, there is a super condition, which we've been writing as SC. So once again, just as we saw with the 10 milliamp, so once again, the 20 milliamp source reduces the number of required loop currents to solve for. So then if I put this all together, here's what we find. We have 3 loops in our counting scheme. We have 1 loop, and this was the 10 milliamp. And now we have a second loop, or excuse me, a second current source, which is the 20. Oops. And those guys reduce it to 1 loop, 1 super loop equation plus 1 super condition equation. Now we can highlight this whole process using the same scheme that we did with the node analysis and voltage sources. So it reads like this. So if we're going to do mesh or loop analysis with current and voltage sources, step 1, we do the same thing as always. We assign a loop current to each independent loop and then determine the number of loop currents. That is, the number of loop equations has to be the number of loops minus the number of current sources. Now we apply the loop equation to each unknown loop current. And when you look at this guy right here is what we've been doing up to now, and this is a regular loop equation. However, if a current source is not isolated from the loops, then we form a super loop. So a super loop, we have to write 2 loop equations into 1 super loop equation. So you could see that I'm going to write the loop equation for loop 1 plus the loop equation for 2, and then I look at the sources around that thing here. So this guy right here is the super loop equation, and this right here is the super condition. That is, it's KCL applied to the current source, which we call the SC equation. So if we write those equations out, we could then solve for all of the loop currents and quantities that we need. So let's apply this to our situation. Okay, so now we want to apply this process to our current example. So let's start from the beginning. So now we've already done this, but let's do this again. So let's do the numbers or the counting. So if I do that, let's set this guy up here. Let me see. I don't know if I have this equation, but I'm gonna take it just in case. And I'm gonna stick it back down here. So when I look at it, I have this. And it looks like I dropped the bottom wire. So let's get that. So if I do the counting, I'm going to see that I have 3 loops, but I have 2 current sources. So that gives me 1 super loop equation for I2 and I3 plus 1 super condition between I2 and I3. So then when I add these up, I have 2 equations and 2 unknowns, where my unknowns are I2 and I3. So then I apply those two. So here we go. So the first equation is the super loop. So I have the super loop between I2 and I3. So then I start going. So I look at loop 2. So if I look at loop 2, I have 10 plus 4. That's the times I2 minus any mutuals. There's a 10 here that's a mutual. And we're going to multiply that by that loop current, but we already knew that, which was minus 10. So when I look at this, this is my first loop equation. So this is loop 2. Now I write the second loop equation in the super loop rule here. So this will be, I have 6 and 8, so I'm going to get 6 plus 8. And then I'm going to multiply this by I3. There's no mutuals. So then when I look at this, this is loop 3. And then I ask, are there any voltage sources around as I go around that purple loop, the super loop? And I see none. So this just tells me that there's no voltage sources in that loop. So when you look at this, look what I have. The super loop equation is 1 equation and 2 unknowns. And in this case, we know that the unknowns are I2 and I3. We need the supercondition equation to set up 2 equations with 2 unknowns. So when I look at that supercondition equation between I2 and I3, then I see that from what we wrote earlier, again, looking at the current source, we see that the I3 is in the direction of the current source. So then that tells us that this is now this guy. So that's our second equation. So now if I write these out into matrix form, so now organizing these equations into matrix form, we then find that we get something like this here. So if I isolate I2, you could see that I2 has 10 plus 4, and it has minus 1. So then I'm going to go 10 plus 4 and minus 1, and that's going to be I2. So then if I look at I3 here, you could see that the top I3 is going to be 6 plus 8, and then from equation 2, I'm going to get plus 1. So in this case, this is I3. So then this is I3, this is I2. Now I look at all of my constants. So if you look at the constants, look at this. I got the 10 times the 10, so I get minus was a plus. If I take it to the other side, I'm going to get a negative sign. So I'm going to go minus 10 times 10. That's the constant. And on the right side of the supercondition, we see that it's 20. So now if I do the matrix magic, I'm then going to find that I2 is then going to be minus 13.6 milliamps, and I3 is going to be 6.43 milliamps. And that is our solutions right there for the loop currents. So just to be on the safe side, let's put these all together here, and we're going to ask, what are the resistor currents? So the first thing that I'll do is that we have to set these guys up so that it looks something like this here. So I'm going to copy this. And I'm going to move this. Oops. So what I would see here is that, note that I2, excuse me, the 2K here in the left loop, we could see here that that's isolated with the 10 milliamps. So that immediately tells us that I2K has to equal this minus 10 milliamps because it's isolated. Now look at the I4. The I4 is also isolated. So if I look at the I4K, that's isolated with I2. So then I2, we see here that that has to be minus 13.6 milliamps. And the other thing that we could see here is that loop 3 isolates the 6K and the 8K, so I could then say that the current of the 6K is going to be the same as the 8K, and that guy is then going to be 6.43 milliamps. So the only one that we really have to worry about is the 10K in the middle here. So if I look at that 10K, here's what we see. So the 10K, according to our loop equations, we're seeing that if I look at the current, I'm going to pick a direction of current. What do I think is the right current? I'm going to say that the current, I think, is going to be plus minus like that. I'm just going to pick a direction. So if I do that, then I see that the superposition of the currents tell me that this is going to be 10 milliamps minus I2, but I2 we see is minus 13.6 milliamps. And when I add these two, I'm seeing that this guy has to be a positive 3.6 milliamps. So this tells us that the polarity of the resistance, so that is so the polarity agrees with currents. I got a positive polarity, so therefore that current is correct here.